So we shall continue with our discussion on this property of connectedness of sets in metric spaces, and we shall begin with the theorem about the characterization of connectedness in the subsets of real line. Namely, we shall show that a subset of a real line is connected if and only if it is an interval. Okay. So let us begin with that theorem. Okay. So this is a theorem. Suppose A is a subset of R, then what we want to show is that A is connected if and only if A is an interval. Okay. As usual, let us first assume that A is connected. Now as we have seen that if A is not an interval, then there should exist three numbers x, y and z such that x less than z less than y, and x and y belong to A but z does not belong to A. Okay. So if A is not an interval, there exists three real numbers x, y, z such that x less than z less than y, x and y belong to A and z does not belong to A. That is the meaning of saying that A is not an interval. Okay. In this case we should show that A is not connected, that will contradict this, that assume that A is connected. And to show that A is not connected, we should produce two open sets G1 and G2 satisfying all those properties. Okay. And in this case it is easy, let G1 be equal to minus infinity to Z and G2 be equal to Z to infinity. Then G1 and G2 are disjoint and their union is in fact R minus this Z. Okay. G1 and G2, and since Z does not belong to A is contained in the union. So A is contained in G1 union G2, and as far as A intersection G1 is concerned, since x belongs to A and x also belongs to this interval G1, so x belongs to A intersection G1, so x belongs to A intersection G1, so this is non-empty. Similarly, y belongs to A intersection G2, that is non-empty, and all these things show that A is not connected. Okay, and that is a contradiction to the assumption that we started with. Okay, all right. Now let us look at this way. Assume that A is an interval. A is an interval. Okay, and if A is not connected, again there should exist two open set G1 and G2 with the required property. Okay, if A is not connected, there exists open sets G1 G2 such that, okay, we have all those required things. First of all, they are disjoint, G1 intersection G2 is empty. Okay, and A intersection A, so A is contained in G1 union G2 and it has non-empty intersection with both the sets. Okay, A intersection G1 is non-empty and A intersection G2 is also non-empty. Okay. Since A intersection G1 is non-empty, we can consider some real number belonging to that. Okay, so let x belongs to A intersection G1 and similarly y belongs to A intersection G2. Okay. Since x belongs to G1 and y belongs to G2, they must be different. Okay, x and y cannot be the same. Okay, so x not equal to y. And as we have seen, if x is not equal to y, since they are real numbers, either x is less than y or x is bigger than y. Okay, we can assume any one of those things. So assume x is less than y. Okay, all right. Now x and y both belong to A, x is less than y, and we have assumed that A is an interval. That means all the points lying between x and y must be in A. Okay, or this is same as saying that this closed interval with the endpoints x and y, that must be completely contained in A. Okay, that is because of our assumption that A is an interval. Okay, all right, and A is contained in G1 union G2. Okay. Okay, so in particular this interval is contained in G1 union G2. Okay, so now what we do is that we consider the intersection of this interval with this first set G1. Okay, right. So consider G1 intersection xy. Okay, then we observe two things. This is non-empty, non-empty because x belongs to this interval, also x belongs to G1. Okay, so this is non-empty, and it is bounded above because this set is bounded above. So for every element in the intersection, in particular it belongs to this also, so y is an upper bound. Okay, so this is non-empty and bounded above, and bounded above. Okay. Oh, all right. If it is non-empty and bounded above, then we know that by LUB axiom, every set which is non-empty and bounded above must have a least upper bound. So let us call that least upper bound to be Z. Okay. So let Z be LUB of this set G1 intersection XY. Okay. All right. Now first of all, let us see where this Z should lie. Okay, and that in fact the crux of the proof is on that. Okay, first of all, Z is the least upper bound. Okay, and Y is an upper bound. Okay, so Z must be less than or equal to Y. Okay, so okay, Z is LUB of F since Y is upper bound of this G1 intersection XY. Every upper bound must be bigger than or equal to least upper bound. So Z is less than or equal to Y. Okay. On the other hand, X belongs to this set. Okay, X belongs to this set, and Z is an upper bound. Okay, so X must be less than or equal to Z. Okay, right. So since X belongs to this, since X belongs to G1 intersection XY, and Z is a least upper bound, we have X less than or equal to Z. Okay, that means what? X less than or equal to Z less than or equal to Y. Okay, so X less than or equal to Z less than or equal to Y. Okay, okay, let us just try to visualize this. So this is an interval XY, so Z is somewhere here, Z lies somewhere in the interval, and this whole interval lies in G1 union G2. Okay, this whole interval lies in G1 union G2. Okay, so Z must belong to G1 or Z must belong to G2, right? Let us see the consequences of both of these. Okay, suppose Z belongs to G1. Suppose Z belongs to G1. Okay, then G1 is an open set, G1 is an open set, so it must contain an open ball with center at Z, and in the real line open balls are nothing but open intervals. So we can say that, so since G1 is open, we can say that since G1 is open, there exists R bigger than 0 such that this interval Z minus R to Z plus R, that is completely contained in G1. Okay, all right. Okay. Now z minus see z is the least upper bound, okay, z is the least upper bound, and z minus r is a number which is strictly less than that, okay. So that means what, there should exist some number which is strictly bigger than this, okay. Okay, since z is the least upper bound and z minus r is strictly less than that, so we can say there exists, let us say, some number, suppose I call that number x1 in this interval g1 intersection xy, such that, so you can say that there exists x1 belong to this g1 intersection xy such that z minus r is less than x1, okay, such that z minus r is less than x1, okay. Okay, fine. So let me leave this argument here. Let us see what happens if z belongs to G2, okay, alright. So suppose now z belongs to G2, okay. If z belongs to G2, again we can say that there will exist some positive number such that open interval with the center at z is completely contained in G2, okay. Then since G2 is open, there exists epsilon, instead of r let me call here it epsilon, such that z minus epsilon to z plus epsilon, okay, is completely contained in G2, okay. Z minus epsilon to z plus epsilon is completely contained in G2, okay, alright. Now if z minus epsilon to z plus epsilon is completely contained in G2, what we can say is that again let us make this same argument here. Since z minus epsilon is not an upper bound, okay, there exists a number, suppose I call that number x2, such that that number x2 belongs to this interval G1 intersection, this set G1 intersection xy, and it must be strictly bigger than z minus epsilon, okay. So we can say there exists x2 in G2 intersection xy, sorry, G1 intersection, because remember z is the least upper bound of this set G1, okay. So any number smaller than that is not an upper bound. So if you take any number smaller than that, there should exist some element here which is strictly bigger than that number. That is an argument we are using, okay. So there exists x2 in this set such that z minus epsilon is less than x2, okay. Of course x2 is less than or equal to z, x2 is less than or equal to z, because x2 is in this and z is the least upper bound, okay. In other words, this x2 belongs to this interval which is completely inside G2, okay, which is completely inside G2. So and also x2 belongs to G1 because of this, right. So see this implies in particular that x2 belongs to G1, okay, right, and that part implies that x2 belongs to G2, okay. Now this cannot happen because G1 intersection G2 is empty, okay, G1 intersection G2 is empty, okay. So Z belongs to G2 is not possible, okay, Z belongs to G2, so this is a contradiction, okay? This is a contradiction, okay. All right, okay, all right. Now in a similar way, is this clear, this part is clear? In a similar way we can get a contradiction here, okay. See actually now in this case we should have considered this part z to z plus r. Okay, suppose we take some number lying between z to z plus r and also which is in this interval, okay, also which is in this interval, then see let us say that, see, it is clear that since this whole interval is contained in G1, see, r cannot be strictly bigger than y because z is a least upper bound. Okay, z is a least upper bound. Okay, all right. So if you take any number which is, let see, this z plus r can be somewhere here. Okay, z plus r can be somewhere here. So suppose we take some number lying between z and y and z plus r. Okay, that is what I want is you add some number to it which is which should be less than both, okay, y as well as z plus r. Okay, suppose you do that, suppose that number is what I call x1. Let us say consider x1 such that, okay, I think let me remove this part. Okay, okay, so consider x1 such that x1 is let us say z is less than or equal to x1, z is less than or equal to x1, it is strictly less than both z plus r and y. Okay, let us say minimum of z plus r and y. Okay, right. Okay. In fact, I can take strict inequality here. Okay, z is less than x1 and that is strictly less than z plus r and y. Okay, right. Now this, since this x1 is less than z plus r, it is in G1. Okay, it is in G1. Okay, right, but it is not in it is in G1, and in a similar way we can show that this x1 since it is strictly bigger than z, remember, okay, this x1 is strictly bigger than z, okay, and z is the least upper bound. Okay, z is so x1 cannot be in this set G1 intersection xy. Okay, x1 cannot be in this set. Okay, that means it has, but this whole interval is contained in G1 union G2, so x2 must be in G2. So again a contradiction. Okay, that is this, sorry, this x1, we have shown that the x1 is both in G1 as well as in G2, so that is again a contradiction. Okay, so contradiction to what? Contradiction to z belongs to G1. Okay, so this contradiction show that z does not belong to G1, and this argument show that z cannot belong to G2. Okay, okay, but z is in this interval x to y which is contained in G1 union G2. Okay, now what is the basic source of all these contradictions? It is this assumption that A is not connected. Okay, right, we are, because we have assumed that A is not connected, we have got the sets G1 and G2 with these properties, and so that has led to all this. So this must be false, so that means A is connected. Okay, then let us proceed to the other theorem which I had mentioned yesterday. It is about the union of connected sets. Okay, right. So suppose XD is a metric space, okay, and let us say that we have taken a family of connected sets, say AI, let us say I belonging to big I. Big I is a what we have called indexing set, it is an indexing set. So let us say this is a family of connected subsets of X. Connected subsets what we want to show that if intersection of these is non-empty, then their union is also connected. Okay. So let us say connected set such that intersection AI, I belonging to I, is non-empty, then union AI belonging to I is connected. Okay. Okay. Let us look at the proof. Now this is fairly straightforward. Let us give some notation for this union. Okay. So let A be equal to union AI, I belonging to I. We shall just see what happens if A is not connected, okay, and then get some contradiction. Okay. So if A is not connected, okay, I think I can just use this. If A is not connected, then there exists open sets G1 G2 such that G1 and G2 are disjoint. A is contained in G1 union G2, A intersection G1 and A intersection G2 both are non-empty. Okay, all right. Okay, all right. But A is a union of these sets. Okay, so if A is contained in, and let us see what follows from that. Okay, so consider one AI, consider one such AI. So consider one such AI for some I belonging to I. Okay. Okay. Now, since AI is a subset of A, because A is a union of all such AIs, okay, and this is contained in G1 union G2. Okay. So AI is contained in G1 union G2. Okay. Okay. G1 union G2 are disjoint, that is something that we already know, okay, right. And let us look at now AI intersection G1 and AI intersection G2. Okay. If both of these are non-empty, then what is the meaning of that? See, suppose you have two open sets G1 and G2 which are disjoint and AI is contained in their union, and if AI intersection G1 and AI intersection G2, if both of these are non-empty, that means that AI is not connected, right, that means that AI is not connected. Okay. That is not, but our assumption is that each AI is a connected. Okay, remember here, okay, our assumption is that each AI is connected. Okay. So that means it cannot happen that both of these are non-empty. Okay, it cannot happen that both of these are non-empty. Okay. So at least one of them must be empty. Okay. So what is the argument here now, that since AI is connected, one of AI intersection G1 or AI intersect, okay, we can simply say AI intersection G1 is empty or AI intersection G2 is empty. Okay. Remember, none of these AIs can be an empty set. Okay, because in that case this intersection would have been empty, right. Okay, so each AI is non-empty. Okay, but what is the meaning of this? Suppose AI intersection G1 is empty, but AI is contained in G1 union G2. So if its intersection with G1 is empty, then it must be contained in G2. Okay. Similarly, if its intersection with G2 is empty, then it must be contained in G1. Okay. That means AI must be contained in G1 or in G2. Okay. So this means that is AI is contained in G1 or AI is contained in G2. Okay. So what did we show? if we take any of these sets in the family, each AI is either contained in G1 or it is contained in G2, okay, alright, okay. Now let us see what are the possibilities. It can of course happen that some of the AIs are in G1 and some of the AIs are in G2, okay, okay. But if that happens, is this possible? Okay. See, G1 intersection, G1 and G2 are disjoint, okay. Suppose some of the AIs are contained in G1 and some of the AIs are contained in G2, then their intersection will be empty, right, okay. So since this is non-empty, all of them must be either contained in G1, okay, or all of them must be contained in G2, right, okay, alright. But suppose all of them are contained in G2, let us say all of them are contained in G2, but that will mean that A is contained in G2, okay, and that will contradict this, that A intersection G1 is non-empty, okay. On the other hand, if all of them are contained in G1, then A is their union, okay, then that will mean that A is contained in G1 and that will imply that A intersection G2 is empty, okay, right. So whatever you do, that will lead to a contradiction, okay, right. And again, what is the source of this contradiction? Our assumption that A is not connected, okay? A is not connected, okay. So that completes the proof that if each AI is a connected set, and if you take, and if the intersection of all this family is non-empty, then the union over that family again is a connected set, okay. Then what we also want to know is what is the relationship between, suppose A is connected, then what can we say about A closure? And it should be, and one can expect that A closure should also be connected, okay. In fact, we will prove something more, okay. Any set which lies between A and A closure is connected, okay. If A is connected, so let me just state that, okay. Okay, again let us start from, so this is again, these things are true in any arbitrary matrix space. Remember, the earlier theorem we had proved for the sets in the real line, okay, whereas this is true in any matrix space. So again let us say xt is a matrix space, okay, then, and let us say suppose A contained in X is connected and there is another set B such that A is contained in B and B is contained in A closure, then B is connected, okay. Okay, so even before discussing the proof of this, you can see one of the obvious consequences of that is that if A is connected, then A closure is connected, right, because in that case you can take just B as equal to A closure, okay. So I can just write a quick corollary of this, okay. A is connected, this implies A closure is connected, okay. All right, now let us look at the proof of this, okay. We need to show that B is connected, so we start with the usual way, okay. If B is not connected, then there should exist two open sets G1 and G2, etc., okay. So if B is not connected, there exists open sets G1, G2 such that G1 intersection G2 is empty, okay. B is contained in G1 union G2 okay, and then B intersection G1 is non-empty, and B intersection G2 is also non-empty. We will show from here that if this is the case, then A also cannot be connected, okay, and that will be the contradiction to the assumption that A is connected, okay. Alright. To show that A is not connected, we have to again consider the open sets, construct open set G1 G2 satisfying all these properties, just B replaced by A, okay. Now as far as this is concerned, there is A is not involved, G1 and G2 are disjoint anyway, okay, but can you see that this implies that A is contained in G1 union G2, okay, because A is contained in B, and if B is contained in G1 union G2, that will say that A is contained in G1 union G2, okay. Alright. The next question is this: from here B intersection G1 is non-empty, can I say that, does this imply that A intersection G1 is non-empty? Okay, this is the question, okay. Okay. What is the answer? See, remember here, okay, now in this we have used this part that A is contained in B, okay, we have not yet used this part B is contained in A closure, okay. Every point of B is a closure point of A, right, every point of B is a closure point of A, okay. So let us start from here, okay. So B intersection G1 is non-empty, that means there exists some point in B intersection G1, okay. So there exists, let us say, X in B intersection G1, okay, B intersection G1, okay. So this X belongs to B and it also belongs to G1, okay. Now okay, since X belongs to G1 and G1 is an open set, okay, X belongs to B1 and G1, so we can say that there exists an open ball with center at X which is contained in G1, okay. So this implies there exists R bigger than 0 such that UXR is completely contained in G1, okay. Can you see what is the next obvious thing to do? X is in B, okay, which is in A closure, so that means X is a closure point of A, and so every open ball with center at X should have a non-empty intersection with A, okay. So every open ball with center at X should contain a point from A, okay. Okay, so since next thing is, since X belongs to B which is contained in A closure, what we must have is that UXR intersection A is non-empty, okay. Now what is the meaning of that? UXR intersection A is non-empty, consider some point in that, okay. So let Y belong to this, let Y belong to UXR intersection A, okay. Okay, does it mean that Y belongs to A in particular? Okay. Does it also means that Y belongs to G1? Because UXR is completely contained in G1, okay. So and Y is in UXR, so it is contained in G1, okay. So these two things imply that Y belongs to G1 intersection A, okay, right. So what did we show? Starting from the fact that B intersection G1 is non-empty, we showed that A intersection G1 is non-empty, okay. So this is true, here is the proof, right, okay. In a similar way, from the fact that B intersection G2 is non-empty, you will be able to show that A intersection G2 is non-empty, okay. So similarly from here this will imply that A intersection G2 is non-empty, okay. But again, so what is, let us again take the stock, what does it mean? G1 and G2 are disjoint, A is contained in G1 union G2, A intersection G1 is non-empty, A intersection G2 is non-empty, which means that A is not connected, okay, and that is a contradiction, okay, right, okay. So whenever A is connected, its closure is also connected, okay, and not only that, any set which lies between A and A closure is also connected. Okay, now let us consider one important concept which is associated with this idea of connectedness. A given metric space may or may not be connected, okay, but it will always have connected subsets, okay. For example, singleton set is always connected, okay. Singleton set is always connected, but we have also seen examples of the sets which are not singleton and still connected. So one can ask a question, can we think of something like a maximum possible or biggest possible connected set, okay. We have seen here, for example, if A is connected, then A closure is also connected, so that is one way of enlarging connected sets, okay. What is the other way? What you can do is that suppose you start with a connected set, okay, then you think of all those connected sets which have non-empty intersection. For example, if you take a family like this, suppose you take all connected sets which contain a given connected set, or in particular you start with a point and consider all the connected sets which contain that particular point, then their union also must be connected, right, okay. So that way we can form new and new connected sets, okay. So the question is, suppose you reach a stage beyond which you cannot extend, suppose you reach a stage beyond which you cannot extend, then obviously such a set will be called a maximal connected set, okay. Set will be called a maximal connected set, and that is called connected component, okay. It is called connected component. Okay. Is the definition clear? Connected component. Connected component is another way of saying that is, it is a maximal connected set. Okay. Again, recall our idea of the maximal elements, okay, right. Suppose you take all the connected sets, okay, then there is this inclusion is a partial order in that, so it is maximal in that sense. Or to make it, so when will we say that a set is a connected component? It means it is a maximal connected set, it means it is connected, okay, and it is not properly contained in any other connected set, right. That is the meaning of maximal connected set, okay, right. Let me repeat again, a maximal connected set means first of all it must be connected, okay, and it is not properly contained in any other connected set, okay, that is a component, okay, right. And what we can show is that even if a given metric space is not connected, we can write that metric space always as a disjoint union of its connected components, okay. Of course the things can be very bad, okay. For example, if you look at the discrete metric space, okay, if you look at a discrete metric space, then it is clear that a singleton set is connected, but if you take any set containing 2 points, it is disconnected, okay, which means in the case of discrete metric space every singleton is a connected component, okay, you cannot do anything better than that, okay. So that is a space we can say, or that is a kind of thing which is as much opposite to being connected, okay. So things like that are called totally disconnected, metric spaces like that are called totally disconnected. Of course this is not exactly what the definition of that, but that is the idea, okay. Totally disconnected means given any 2 distinct points you can find what is called a disconnection of, okay. I have not defined this word disconnection, but let me just say again, okay, what is meant by disconnection. Suppose a metric space is itself not connected, okay, then what should happen? This whole space is X, and if that is not connected, then it should be contained in 2 open sets G1 and G2, that is X is equal to G1 union G2, and then G1 intersection G2 is empty, and G1 and G2 both are non-empty, okay. See, normally we would have said G1 intersection X is non-empty, but G1 intersection X is just G1. Okay. Similarly, G2 intersection X is simply and X is, we would have said X is contained in G1 union G2, but that is same as saying that X is equal to G1 union G2. So if the metric space itself is not connected, then you can find two open sets satisfying this. So this G1 G2, that is called a disconnection of X. Okay, that is called a disconnection of X. If such sets exist. Okay. Of course, given a metric space there could be several disconnections. Okay. Given a metric space there will be several disconnections. Okay. Like for example, if you take a discrete metric space, okay, you can take G1 as one singleton set and G2 as its complement. Okay. That will be a disconnection. Okay. And well, you can do it for each single point, so there will be several disconnections. So what is meant by totally disconnected metric space? It is that given any 2 points of that space, you can find a disconnection such that G1 contains one of those points and G2 contains the other point. Okay. That is, in other words, any 2 distinct points can be separated by a disconnection. That is what is called totally disconnected metric space. And the example of that which we have seen till now is the discrete metric space. There are many other examples also. Okay. For example, if you take the set of all rational numbers, okay, that is also set of all rational numbers as a metric space. Okay, not as a subspace of R, but as a metric space itself. Then there also you will see that that is also an example of a totally disconnected space. Then let me just say, how does it follow that every metric space can be written as a disjoint union of its components? What we can see is that, okay, let us say, first of all, is it clear that okay, let me just say, suppose XD is a metric space, okay, and suppose C is a connected component. Okay, we can see some of these properties of C. Is it obvious that C must be closed? Is it clear? Okay. Remember, we have already shown that if C is connected, then C closure is connected. Okay, and so if C is maximal, that means C is not properly connected in C closure, which is same as saying that C and C closure must coincide, right? Okay. So if C is a connected component, then C is closed. Okay. All right. Secondly, suppose you take 2 connected components, C1 and C2. Suppose C1 and C2 are connected components. Okay. Then either they should be disjoint or they should be same. Okay, right? You can see again why. Then we can say then C1 intersection C2 is empty, or C1 is equal to C2. Okay, that is, if this is non-empty, or which is same as saying that is if C1 intersection C2 is non-empty, then C1 is equal to C2. Okay. How does this last thing follow? Suppose this is non-empty. Okay, then you look at C1 union C2. Okay, if C1 intersection C2 is non-empty, then C1 union C2 must be connected. Right? If C1 union C2 must be connected, C1 and C2 both are components. We know that C1 is contained in C1 union C2. That is, C1 is contained in C1 union C2, and C1 intersection C2 is non-empty. This is a connected set, but if this is maximal, this must coincide with C1 union C2. Right? Okay. So C1 must be equal to C1 union C2, and similarly C2 must be equal to C1 union C2. because C2 is also connected component, C2 is also maximal connected set, so it cannot be properly contained in any other connected set, and C1 union C2 contains C2, that means these two must coincide, right. Okay. So any two connected components, either they are the same or they are disjoint. Okay. Then since a singleton X is a connected set, what we can do, as I said just now, take all the connected sets which, let us say, suppose you start with a point, let us say X belongs to X, okay, or let me say X naught belongs to X, okay. Then take all the connected sets which contain X naught, there certainly one such set exists, that is singleton X naught, okay. So take all the possible connected sets which contain X naught, then consider their union. Since all of them contain X naught, their intersection is non-empty, okay. So their union must be connected, okay. Their union must be connected, okay, and that will be a connected component, okay, because if any other connected set contains that union, it also must contain X naught, which means it is already a part of the family, okay, right. So every singleton point X naught is, every point X naught is contained in some connected component, okay. So which is same as saying that X can be written as a union of connected components, okay, right. Okay. So even though the matrix space itself, let me again repeat, even though the matrix space itself is not connected, we can always write it as a union of its connected components, and any two such, all these components are closed, and any two distinct components are disjoint, okay. So a matrix space can be written as what is called a disjoint union of its connected components, okay. Now while discussing completeness, we also proved what is called Banach's contraction mapping principle, okay. As we said, that is an example of what is called a fixed point theorem, okay. It's a theorem which says that certain map has a fixed point, okay. Now connectedness also leads to some fixed point theorems, okay. Let me just give an example. We have, using the fact that a set in a real line is connected if and only if it is an interval, we have proved what is called intermediate value theorem, okay. And what does the theorem say? That if a function takes any two values, suppose a function goes from a connected set to real line, and if it takes any two values, then it takes all the values in between those two values, okay. That is an intermediate value theorem, okay. Using that, we can say that, suppose let us say f is a function, let me take, to begin with, the interval, let us say 0 1 to 0 1, it is not very important, it can be any interval ab to ab. Suppose f from 0 1 to 0 1 is continuous, okay, then f has a fixed point, okay, and this follows in a very straightforward manner by an immediate application of what is called intermediate value theorem, okay. So how does it follow? We can just consider a function, let us say gx is equal to fx minus x for x in 0 to 1, okay, okay. Then what is g0? Okay, first of all, then G is continuous, okay, then G is continuous, okay, G is continuous, G0 is f0 minus 0, right, okay, and f goes from the interval 0 1 to 0 1, so f0 is some number lying between 0 and 1. So is it clear that f0 minus 0 must be bigger than or equal to 0, right, f0 minus, so this is bigger than or equal to 0, okay, alright, okay. Now similarly I look at g of 1, okay, so g of 1 will be what? It will be f1 minus 1, right. What can you say about this? again remember f goes from the interval 0 to 1 to interval 0 to 1, so f1 lies between 0 and 1. So what can you say about f1 minus 1? It must be less than or equal to 0, right? It must be less than or equal to 0. Okay. So g is a function which is bigger than or equal to 0 at 0 and it is less than or equal to 0 at 1. So what does intermediate value theorem say? It means it must take, it means it must be, see, suppose this is strictly bigger than 0, or if it is 0 there is nothing to be proved. Okay, suppose one of these values are 0, then that is what we want. Okay, so we can say that these two things will imply by intermediate value theorem, there exists, we can say, some x naught such that g of x naught is 0. Okay, but if g of x naught is 0, okay, that is same as saying that fx not equal to x naught, right? G of x naught is 0 is same as saying that fx naught is equal to x naught, okay, right? So where did we use connectedness? In applying this intermediate value theorem, okay, right? Now you can see a few things here. There was nothing particular about this interval 0 to 1. The same argument would have worked if you replace this interval by any other closed interval, ab to ab, okay, alright. And for example, I could have taken minus 1 to 1 instead of 0 to 1, I could have taken minus 1 to 1, okay, and that is what leads to another important theorem. I will just state that theorem. We shall not discuss the proof of this because that is fairly complicated. It is a very well known theorem. It is called Brouwer's fixed point theorem. Brouwer's fixed point theorem. Okay. So instead of this interval 0 to 1, we take what is called a closed unit ball in Rn. Okay. Closed unit ball in Rn. Suppose I call that ball as B. Let us say, what is a closed unit ball in Rn? It is the ball with center at 0 and radius 1. Okay, so it is a set of all x in Rn with norm of x, whatever norm you take here. Okay, norm of x less than or equal to 1. Okay, you can take any norm here. So for the time being, let me just take the usual Euclidean norm, norm x of x2 less than or equal to 0. Okay, and let f from B to B be continuous. Okay, then f has a fixed point. Okay. As I said, proof of this involves lots of advanced techniques, so we shall not go into this proof here in this course, but we can see that this is a special case of Brouwer's theorem. Okay, if I take the interval minus 1 to 1 here instead of 0 to 1, that is nothing but the closed unit ball of R1, right, closed unit ball of R1. So in this case the proof is easy, but in any other cases proof is complicated, so we shall not discuss it here. And you can compare this theorem with contraction mapping principle. You can see that here we have only assumed, here as well as here, only assumption is that f is continuous, whereas in the case of contraction mapping it was that it is a contraction. Okay. But of course conclusion is also weak. Okay, we have only said that it has a fixed point, whereas in the case of contraction mapping we had said that it has a unique fixed point. Nothing is said about uniqueness here. Okay. Nothing is said about uniqueness here. So hypotheses are weaker, conclusion is also weaker. Okay. We'll stop with that.